Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or tutoring, check out the links in the description below. So let's get started on our questions for today's session. Okay, so I'm not sure if you can read it, but I'll just read it out loud. Match the following properties of liquids to what they indicate about the relative strength of the intermolecular forces in that liquid. And then they want me to just sort out what are the causes of strong intermolecular forces and what are the causes of weak intermolecular forces. So let me just write down the definition of the two. Strong and I'll just make like a comparison table. So basically, when you have strong intermolecular forces in the liquid, that means that you have very strong bonds that are present in the liquid. And then on the other hand, for the weak intermolecular forces, that means you have weak bonds. So then if you try to think about the properties of liquids that have strong bonds, they're much harder to boil since they're stronger. So they have high boiling points. They also have high surface tension. And lastly, they also have high viscosity. And the only property of liquid that is in the weak intermolecular forces section would just be the high vapor pressure. Okay, so let's check out the answers from our junior tutor. Strong, high surface tension, high boiling point, and high viscosity. Weak, high vapor pressure. So this solution is correct. Okay, so let's move on to question number 2. Which has the highest vapor pressure? 20 grams of glucose, 20 grams of sucrose, or 10 grams of potassium? I think that's potassium acetate. Anyways, let's just try to answer it. So for high vapor pressure, we want to look at Raoult's law. And basically this law is pressure is equal to P naught times X. Where P naught is the vapor pressure of pure solvent And then X is the mole fraction. Okay. So now I'm just going to calculate the number of moles of each of these solutions. So let's look at glucose first. It is C6H12O6. To calculate the number of moles, it's going to be mass over molar mass. So since we have 20 grams of glucose, its molar mass is actually 180 grams per mole. So this gives us a value of 0.11 moles of glucose. Now let's look at sucrose. So it's C12H22O11. There are 20 grams of sucrose, and its molar mass is 342 grams per mole. So you get 0.058 moles. Okay, so now let's look at potassium acetate, which is, they wrote it as KC2H3O2. So its number of moles, 10 grams divided by, let me look up the molar mass of potassium acetate. .14. Then to calculate for the moles, it's going to be 10 divided by 98.14, and you get 0.10 moles. Okay, so now if we assume that we dissolve each of these solids in like separate mixtures of water, let's say in like 100 mils of water, the one with the highest vapor pressure has the least number of moles. So in this case, it's the sucrose. Okay, so that's because the sucrose has the least number of moles. Let's look at the answer. Obviously, there are less moles of sucrose in the same amount of water, so the sucrose solution have the highest vapor pressure, and the potassium acetate will have the lowest. So here they just said 20 grams instead of the 10 grams. That's why they got half the amount of moles. But still, the potassium acetate solution will have the least. Answer is correct. But there's only 10 grams of potassium acetate. N is equal to 0.10 moles. But solution is still correct. Okay, so let's move on to question number 3. Which of these structures has the most angle strain? Which has the most steric strain? And which of these structures has the most torsional eclipsing strain? So let's draw out all these different molecules. I was never good at drawing these chair configurations. And it looks like each of these just has like a methyl group coming out of it. Then this is a staggered butane. Okay, so this is 1,1-dimethyl cyclobutane. I'll denote it as A. B is 1,1,3,3,5,5. Hexamethyl cyclohexane. And then this one is just staggered butane. Let me just move this over a bit so that you can see it. On. So there's a hydrogen there, and then just another methyl group there. So the first question asks, which of these structures has the most angle strain? So the structure that will have the most angle strain is the one that has the most deviation from an actual tetrahedral bond angle. So this angle is 109.5 degrees. So let's look at all of the structures. So A has a 90-degree angle in there. B, this is 120. And then if we look at the angle of the staggered butane, it's the 109.5 degrees. So therefore, the one with the most angle strain is structure A. Okay, so part B. Which of these structures has the most steric strain? Okay, so here is when the interactions between substituents so basically when you have bulky groups all close together, okay, so if you look at all of our structures, there's some steric hindrance here, but if you look at B, it has all these methyl groups like kind of pointing out. So therefore structure B has the most steric strain. And you can already see with the staggered butane that there's not much strain on it. So the answer for B is structure B. And then which of these structures has the most torsional strain? So this is determined by the repulsion between bonding pair of electrons. And it's present in the molecule with eclipsing conformation. Okay, so I'm gonna draw out structure A, just kind of with all the hydrogen groups put in. And you can see it has this kind of like puckered ring structure, which causes eclipsing interactions. So the answer for this one is also structure A. Let's look at the answer from our junior tutor. 1,1-dimethylcyclobutane has the most angle strain. Yep. Since its bond angle is 90 degrees, the most steric strain is compound B due to the 1,3 diaxial interactions of methyl groups. And then C, torsional strain is caused due to the repulsion of electrons present in eclipsed conformations. Then this is due to the puckered structure of the cyclobutane. So this solution is correct. Okay, so let's move on to question number 4. Rank the following fertilizers in decreasing order of mass percentage of nitrogen. Okay. So to find the percentage of nitrogen, I'm going to use this equation. Which is equal to the mass of nitrogen all over the mass of the compound. So let's look at for A. There's only one nitrogen, and the molar mass of nitrogen is 14. grams per mole. And then the mass of this entire compound is 101.1 grams per mole. So therefore its percentage, if you were to multiply all of this by 100%, is equal to 13.85%. Now let's just do the same thing for all the other compounds. So there is only one nitrogen here as well. Its molar mass is 115.02. So its percent nitrogen is only around 12.17%. Then moving on. So here there are 2 nitrogens present. So I'm going to do 28 instead of 14. And the total molar mass of this compound is 132.14. So this gives a percent nitrogen of 21.18%. That's the highest one so far. Now for D. Again, there's 2 nitrogens present here. And then its molar mass is 80.04. So then this compound has a percentage nitrogen of 34.98. So that's winning now. Now let's look at E. It's just an NH3. So it's going to be 14 over 17 times 100%. So this is now winning 82.35%. And then lastly, let's look at F. So here there are 2 nitrogens, and then its molar mass is 132.06. So its final percentage is 21.20%. So I'm gonna rank these now. From highest to lowest, E is number 1. And then D is number 2. And then F is 3. C is 4. A is 5. And then B is 6. Let's check out the answer from our junior tutor. Okay, so they calculated it the same way that I did. They got 12.17, 21.18, 34.98, 82.35, and then 21.20. Okay, so great job. This solution is correct. For rest, correct. Okay, so looks like number 5 is kind of like a two-parter. The data below were collected for an enzyme-catalyzed reaction. And then they give values of the concentration of the substrate. And then they want you to calculate Vmax and Km for this reaction. And also to graph it. So first I'm just going to write down these concentration values. And then these velocity values. Okay, so now that I have those written down, I'm also interested in finding the inverse of these values as well, since this is what we are going to graph in order to find Vmax and Km. So I'm just taking the reciprocal of both of these values. And then if you were to do 1 over 0.2, you get 5. 1 over 0.5, you get like 3. 1 over 2 is 0.5, and then 1 over 4, 0.25. And let's look at the reciprocal of these ones. You get 1.16. And then let me just see. If I wrote this down right. Is 1 over 0.8. Yeah, so 1.2. And then let's do 1 over 2.22 is 0.45. And then 1 over 3.08 is 0.32. Okay, so now I want to graph these values. I'm going to do it on the right side here. So on the x-axis, I'm going to do the 1 over concentration of substrate. So from 0 up to 5. So Then for the y-axis, it's going to be the 1 over the rate. So let's do it like 0.1. No, that's not going to work. Let's do 0.2. So just like a rough graph, I'm going to try to plot these. And this is not to scale, but basically what you should get in your graph is like this. You should see like a straight line if you were to do this like properly. And what we're most interested in is the equation of this line. So if you were to use like Excel or Sigma plot, you get an equation of this line, which is y equals 0.17x plus 0.3. So basically, 1 over V max is equal to your 0.33 value. So therefore, we can calculate for V max, and it'll be equal to 3.0. And then secondly, for our slope, we know that the slope is equal to Km over V max. And the slope of the line is 0.17. So then subbing in our V max value, you get 0.17 times 3.0. And then our Km value is 0.51 mm. So that's for part A of 5. Just since this is such a different question than part B, let's see what our junior tutor said. So they plotted the reciprocals. They got a different value here, but the rest are right. I think that just from that one mistake, it kind of messed up their math a little bit. I'm just gonna correct them and say the equation of the line should be y is equal to 0.17x plus 0.33. Therefore, V max will be equal to 3.0 over S, and Km will be equal to 0.51 mm. It doesn't look like they answered part B of this question, but I'm just gonna do it right here. (5b). An enzyme has been identified with the active site shown below, drawn as at a physiological pH. You have been asked to design a peptide that binds tightly in this enzyme pocket. Which of the given amino acids are likely to interact most strongly with each region at physiological pH? And then they just give us different options of amino acids. So first let's look at region 1. So this amino acid is cysteine. Cysteine. And then basically, out of all of the options that are given, I would say that out of all of them, then the threonine would interact the most strongly. So let me draw out the structure of threonine, and I'll explain why once I finish writing it down. So you'll see it contains an alcohol group there. And if I were to also draw our cysteine in this way as well, and again, there's a slightly positive hydrogen, slightly negative sulfur. And you can see that hydrogen bonding can take place for these two amino acids. So therefore, since they can form hydrogen bonds, therefore it's threonine. Okay, so now let's look at region 2. So region 2 has like a 2-ring structure. If I don't butcher this. Kind of like that. This is the structure for tryptophan. So you'll notice that there's a benzene ring. There's also an amine group involved. So because of this kind of structure, out of all of the given amino acids, like which one would react the best, I would say tyrosine. So the structure of tyrosine is as follows. Basically, you have your OH group that's attached to a phenyl. Then you just have the remainder of this amino acid. This is tyrosine. So you'll notice that there can be a possible pi-pi interaction. But you'll also notice that phenylalanine also has a benzene ring, but since tyrosine has this extra alcohol group, you could potentially also form hydrogen bonds. So that's why tyrosine was selected. And lastly, let's look at region 3. So this one might be the easiest to figure out. And that's just because it has a negatively charged oxygen. So basically, which one of these amino acids has a positively charged nitrogen? So this is aspartic acid. And then out of the 3 options that they give us, lysine is the one that can have a positively charged nitrogen. So its R group looks like this, and I'm going to draw it with a positive charge just so that we can picture it. And then there's its carboxylic acid group. Here's the NH. This would be positive as well. And then this is lysine. Basically, positive reacts with negative. So I'm also gonna write this down. For the second part of the question, region 1, E3-onine due to H bonding. Region 2, tyrosine due to H bonding and pi-pi interactions. Then region 3 would be lysine due to positively charged. And reacting with the negatively charged O. Yeah, so the junior tutor wrote down the correct work. So let me just say that the work was correct. But 1/0.37 should be equal to 1.16. Okay. And then I also just added the second part of that equation. So that was a long question number 5. Let's go on to 6. For the protons labeled HA and HB, predict the characteristics of their signals in the H&MR spectrum, the approximate chemical shift, the splitting pattern, and also the integration value. This is a 2-part question again. Let me write down this structure. I'm going to use different colors for these different hydrogens. So for HA, I'll use blue. And then for HB, use black. And what they're also missing here is that we can also draw in that there are more HBs over here on that side, and there are also other hydrogens here that are chemically equivalent to HA. So if we were to look at the chemical shifting of like methyl hydrogens in like a chart, you'll see their approximate chemical shift is 1 ppm for CH3. And then if we look at the splitting, if we follow the rule where it's n+1, depending on how many neighbors you have. So for HA, you'll see there are 2 neighbors beside it, so 2 HBs. So if we do n+1, you'll get a triplet as the splitting. And then lastly, for the integration value, there are 6 HAs present, so therefore its integration is 6H. Now let's look at HB. If you look up the approximate chemical shift for CH2s, it's around 1.3 ppm. So you can just get that off like a table. If you look at the number of neighbors it has, there are 3 of the HAs, and then we're going to do n+1 again. So it'll split as a quartet. And then if we were to do the integration, it would be 4H, since there are 4 HBs. So let's look at part B of this question, which asks how many unique H&MR signals exist in the spectrum of the following compound. So I'm going to draw out this benzene ring, and you'll see that there is a chlorine group, and then also there is a methyl group up there. So we already know that these 3 hydrogens will be different from the hydrogens in the ring. I'm gonna draw all of them in different colors. There's a hydrogen there that is right beside a methyl group. So therefore it's chemically different than the hydrogen beside it, which will also be different to the hydrogen para of the CH3, but also closer to this chlorine group. And then this hydrogen would also be chemically different from all of the other hydrogens because it is the closest to the chlorine. So counting out all these different hydrogens, we have 1, 2, 3, 4, 5. So therefore, there are 5 unique H&MR signals. Okay, so let's see the answer from our junior tutor. Okay, so they also noted that the hydrogens here would have the same signals as H and B. They have 1 ppm for HA, split as a triplet, 6H. 1.6 ppm, quartet, 4H. Maybe they just looked at a different table. I'll just make a note of that. And then they also counted out 5 unique H&MR signals. So solution is correct. But the chemical shift of CH2 can be 1.3 ppm. I'm just going to say this solution is correct though, because all the work was correct. Okay, so let's look at question number 7. Which 3 of the following statements are true? The bilayer of a cellular membrane is primarily composed of amphipathic lipids, also known as amphiphilic. So this is true. Bilayer is composed of amphipathic lipids. So I'm going to draw out an example of what these amphipathic lipids kind of look like. Basically, you have a head and then the tail. So usually it's like a non-polar tail. And then the head is polar. And that's what they mean by amphipathic. It has both polar and non-polar attributes to it. Let's look at 2. Forming an ordered network of water around hydrophobic molecules increases the entropy of water. That is false. 3. Nonpolar molecules that have no polar groups can readily form micelles. So this is also false. And I'll say why. Because micelles look like this. So fun fact, micelles are used like in soaps and detergents, and they're the reasons why we can trap dirt in the inside of them and then using water, just washing it out. So basically you need both nonpolar and the polar groups to form micelles. Okay, 4. The tendency of hydrophobic molecules to aggregate in water is called the hydrophobic effect. So this is correct. And then lastly, for 5, placing a hydrophobic molecule into water causes water molecules to orient themselves around it. So this is true. Okay, so let's look at the answer from our junior tutor. The bilayer of a cellular membrane is primarily composed of amphipathic lipids. The tendency of hydrophobic molecules to aggregate in water is called the hydrophobic effect. Then lastly, placing a hydrophobic molecule into water causes water molecules to orient themselves around it. So solution is correct. Okay, so we have time for one more. But this one has like a lot of different mini questions in it, so let's just see how many I can answer in the amount of time we have left. Not that much time, but let's see. What are transferred in an oxidation reduction reaction? These are electrons. In the reaction of beryllium with fluorine, which atom is oxidized? So this answer is beryllium. It goes from a neutral state of 0 to a +2 oxidation state. 3. This equation represents the type of reaction called, so this is an oxidation reaction. And we know this because the silver is oxidized. Or what is the reducing agent in the following reaction? So in this case, it is our potassium. The oxidation number of oxygen when it is in a compound other than a peroxide is -2. So when it's in a peroxide, it has a -1 oxidation number. What is the oxidation number for each atom in NH4F? So the fluorine will have a -1 oxidation number. The hydrogens, each one has a +1. So therefore, our nitrogen will have a -3 oxidation number. So those are the 3. Which atom has a change in oxidation number of +4 in the following redox reaction? So already just looking at this, I can tell that it is the sulfur and SO2. Since there are 2 oxygens, each with a -2 charge, you need a +4 sulfur, and it went from an oxidation state of 0 to +4. Of the following metals, which ions are most easily reduced? So they don't give us the table for this, but basically the answer is copper. In a zinc-copper cell, which electrode is positive? So it would be the copper 2+. Let's look at 10. How must a redox reaction that is to be used as a source of electrical energy be set up? So it should be physically separated. In a voltaic cell, at which electrode does reduction occur? So reduction takes place in the cathode. What assures that there is no charge buildup in a voltaic cell as oxidation and reduction occur? This is the salt bridge. The most commonly dry cell, what material is the electrode that is the center rod made of? That was worded oddly, but the answer is graphite. So graphite is a conductive material used. 14. To charge a lead storage battery, you must apply direct current. In a hydrogen-oxygen fuel cell, the oxygen diffuses through the cathode. When electrical energy is used to cause a chemical reaction, we call this process electrolysis. Which of the following is true about an electrolytic cell? Changes chemical energy to electrical energy. Type of cell used in electrocution. Uses an electric current to make a non-spontaneous reaction go. So that is all of the above. 18. The products formed in the net reaction of the electrolysis of water are both hydrogen, H2, and oxygen. I'm just going to answer this last one. What occurs in electroplating? So this is when you have the deposition of a metal layer on a material. And the rest are just open response questions. So let's see, electrons, beryllium, oxidation, K. I think they did the oxygens in a peroxide. -3, +1, -1. The sulfur, copper. Separated physically, cathode, salt bridge, graphite, direct current. Oxygen diffuses through the cathode, electrolysis. Okay, so yeah. Hydrogen gas and oxygen gas, deposition of metal layer on a material. Okay. I'm just gonna mention that O has a -2 oxidation number when not as peroxide. Solution is correct. Okay, so I went a little over, but basically that's all for our Q&A session today. If you'd like to submit a question of your own, then check out the links in the description below. And also, if you'd like to be notified of when we do this next, then click on the subscribe button and also the notification bell. Don't forget to leave a like and comment if you enjoyed the video, and also just if you wanted to share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.